The scientific method has been the key to the great success of science over the past 300 years, and it's incredibly important to distinguish it from the philosophical method.
Probably learned about the scientific method in 5th grade, and might be surprised that we're doing an episode on it.
But times are changing. There's now a serious controversy in the scientific community about whether it's time to change the definition of science to accommodate the multiverse.
That's a truly shocking development. In this episode, we'll present a clear formulation of the scientific and philosophical methods, so you can see for yourself whether multiverse is science or philosophy. In the past 6 episodes, we've shown that the multiverse fails to explain fine-tuning because the measure problem prevents it from establishing the typical universe premise. Let's now return to multiverse scientists' supports for their first 2 premises. Supports which, for the sake of argument, we granted them in this season's first few episodes.
In episode 3, we granted multiverse scientists their support of the infinite multiverse premise via eternal inflation and its infinite unobservable universes. Then, in episode 5, we granted the validity of string theory and its unobservable hidden dimensions, the only way multiverse scientists can support the varied multiverse premise's claim that the constants of nature change throughout the multiverse.
We didn't grant all of this because we actually think multiverse scientists convincingly provided scientific arguments for the existence of an infinite varied multiverse. Instead, we granted it because we wanted you to clearly understand that as a consequence of the measure problem, the multiverse fails even in its own framework.
Even though we granted multiverse scientists their first 2 premises, many prominent scientists, such as Roger Penrose, Paul Steinhardt, Lee Smolin, and George Ellis, aren't as generous. They dispute the scientific validity of positing an infinite number of unobservable universes or extra dimensions.
In this and the next episode, we'll present these scientists' argument that the multiverse, eternal inflation, and string theory have deviated from proper scientific methodology and should therefore be regarded as science-based philosophy instead of science.
These scientists make a very compelling case that these theories are not science, at least according to the way science has been defined over the past few hundred years. To understand this point, we must understand what the scientific method is and why it's so important.
Much of the great success that science has achieved since the 17th century is directly attributable to the scientific method, largely developed by Francis Bacon, Galileo Galilei, and Isaac Newton. More recently, Albert Einstein identified 3 necessary elements of the scientific method. 1, ideas, 2, observations, and 3, mathematics.
Einstein wrote as follows: fundamental ideas play the most essential role in forming a physical theory. Books on physics are full of complicated mathematical formulae, but thought and ideas, not formulae, are the beginning of every physical theory. The ideas must later take the mathematical form of a quantitative theory to make possible the comparison with experiment.
What's the relationship between ideas, observations, and mathematics? And why are these 3 elements all so essential to the scientific method? To answer these questions, Aaron, let's start with a clear, basic, and simple description of the steps of the scientific method.
Clear, basic, and simple? I'd love to, Ellie, but maybe this is more your thing.
I hear you, Aaron. Here it is. Everything begins with our observation of diverse phenomena in the world around us. Despite the complexity of everything we see, we notice that nature isn't random, but seems to follow simple patterns. Scientists try to make sense of these patterns by formulating theoretical laws that are hypothesized to explain our observations. By rigorously formulating these laws in mathematical language, they assess what new observations these laws predict. Scientists then perform experiments to check if these hypothesized laws conform to reality. If they do, great. If they don't, scientists go back to the drawing board, either adjusting these laws or formulating new laws that do conform to our observations. How was that, Aaron?
It was pretty good, Ellie. Now that we have a basic idea of how the scientific method operates, let's try to get a little more defined and abstract by discussing the importance of all 3 elements and the relationship between them.
We'll start with the first 2, theoretical ideas and empirical observations. Aaron, please explain the relationship between these 2 elements and why they're both so vital to science.
True scientific progress only occurs through the give and take between the theoretical development of ideas and observations of carefully designed experiments. First, observations motivate abstract theories. Then, these theories are developed to the point where they can make new predictions that are experimentally tested. If there are any surprising experimental results, the theories are further modified and the whole cycle begins again.
By the nature of this process, neither observation nor theory can on their own be considered science. On the one hand, imagine a research project that involves extensive observation and experimentation, but never results in a theory that unifies the multitudinous results of the experiments. This isn't science, but rather a type of sophisticated data collection.
On the other hand, imagine many scientists in a room who theorize about the laws that govern our universe, but never attempt to verify their theories through experiments. This too is not science, but rather a type of speculative philosophy.
Now that we understand the importance and interplay of theory and observation in the scientific method, we can see where the third element, mathematics, fits in. Mathematics provides the all-important connection between the first two elements, the theory and the experiment. As Einstein said, ideas must take mathematical form to make the comparison with experiment possible.
When scientists formulate a theory mathematically, they can calculate its precise consequences and make a prediction. They can then test this prediction against their carefully designed experiment and thereby accurately check whether the theory is true or false.
Now that we've explained the necessity and interplay of the three elements of the scientific method, let's discuss the importance of following it.
There are at least two reasons why it's so important to follow the scientific method. One, because it gives us the ability to reject false theories that may be intuitively appealing. And two, it gives us the ability to accept true theories that may be intuitively unappealing.
Let's explain these points one at a time, beginning with how the scientific method allows us to reject false theories despite their appeal.
Throughout history, many people have proposed various theories to explain the world. Some theories have been simple, some complicated. Some beautiful, some ugly. Some mathematical, some not. After centuries of comparing many theories to observation, scientists have found that successful theories have some common properties. Namely, they are generally simple, beautiful, and mathematical.
The prevalence of this pattern may lead to the belief that all simple, beautiful, and mathematical theories are true scientific theories. But this is a mistake. Just because simplicity, beauty, and a mathematical form seem to be necessary conditions of a true scientific theory doesn't mean they're also sufficient conditions.
History has taught us that despite the profundity of a theory's ideas or the beauty of its mathematical formulation, any theory can be wrong, meaning that it doesn't correspond to the observed properties of nature. Roger Penrose, in his book, Fashion, Faith, and Fantasy in the New Physics of the Universe, emphasizes this point as follows. There are many instances of powerful and impressive mathematical theories where there has been no serious suggestion of any links with the workings of the physical world. It is clear that, for a profound new physical theory, we need a good deal more than just this kind of mathematics, despite the subtlety, difficulty, and indeed sometimes even genuinely magical qualities that the mathematics may possess. Physical motivation and support from experiment are essential in order for us to be persuaded that there is likely to be any direct connection with the actual workings of the physical world.
Because there are many examples of theories producing new, surprising, and beautiful mathematics, but having nothing to do with the physical world, the criteria for a theory to be considered scientific must remain its predictions and comparisons with real observations. Philosopher of science Karl Popper famously stated that to be considered science, a theory must be falsifiable. That is, it must make a concrete prediction that enables it to be reasonably tested and proven false by observations.
That doesn't mean that simplicity, beauty, and a mathematical form are irrelevant to the scientific search for truth. As we explained in episode 2 of the Intelligent Cause series, the aesthetic properties of a theory are guides that provide clues to physicists that they're on the right track. But it's important to remember that even though true theories are simple, beautiful, and mathematical, there are even more false theories that are also simple, beautiful, and mathematical.
Since it's vital to root out false hypotheses, scientists demand that their theories make concrete predictions that can be reasonably tested against observations. This demand for falsifiability has allowed science to reject appealing but false theories, and only accept those theories that actually correspond to reality. Therefore, even if a theory involves profound, beautiful mathematics, it's still not science unless it can make a prediction that can be compared to the actual physical world.
We'd like to add that historically, this point has been uncontroversial. It was universally agreed upon by all scientists of prior generations. As physicist Richard Feynman stated in 1956, all scientists will agree that any question, philosophical or other, which cannot be put into the form that can be tested by experiment, or in simple terms, that cannot be put into the form, if I do this, what will happen, is not a scientific question. It is outside the realm of science.
Now that we've discussed the importance of the scientific method in rejecting false theories despite their appeal, let's discuss its importance in accepting true theories, even if they're extremely counterintuitive. We'd like to make 2 points in this regard.
First, as scientists repeatedly test the predictions of a hypothesis and find them consistent with observations, a scientific consensus will form that it's true. This is no small matter. We can see this by comparison to areas of study that aren't subject to the scientific method.
For example, in philosophy, it can be very difficult to ever establish a consensus on what's true and what's false. This often causes conflicting opinions to persist for centuries or even millennia and impedes the accretion of secure knowledge. On the other hand, the scientific method allows scientists to form a consensus about what's true, thereby allowing them to lay solid and agreed upon foundations for building further theories.
Second, the scientific method's ability to experimentally verify theories is so powerful that it enables scientists to accept theories that would otherwise be written off as wild and crazy. Take quantum mechanics, for example. Many strange features of quantum mechanics regularly invoke the sentiment that just can't be true. One example is Schrodinger's famous cat paradox that we mentioned in episode 2. The same cat can be considered simultaneously dead and alive, and quantum mechanics has many other counterintuitive paradoxes. In the words of Richard Feynman, I think I can safely say that nobody understands quantum mechanics.
So, you may ask, if nobody truly understands quantum mechanics, why is it accepted as a legitimate scientific theory? Why is it accorded the esteem and validity of science?
Because quantum mechanics predicts experimental results that would have never been expected if it were false. When scientists test these surprising predictions, of course not with an actual cat, they find that quantum mechanics is consistently confirmed and our old, more sensible theories are contradicted. For this reason alone, a theory like quantum mechanics can be universally accepted as scientific truth, despite its seemingly wild and crazy features. Such is the power of the scientific method.
While the requirement of experimentation is crucial in science, not all areas of knowledge are subject to the scientific method. History, for example, isn't subject to the experimentation that would make it scientific. Nevertheless, we don't shun the study of history, but rather recognize it for what it is, and develop a methodology that's appropriate for it.
The same is true with philosophy, which deals with ideas that aren't subject to observational confirmation, like ethics and logical reasoning. It's important to recognize philosophy for what it is and to develop a methodology that allows us to arrive at clear and reasonable ideas, even without the ability to compare them to experiments.
The fact that philosophical theories don't make testable predictions doesn't make it a free-for-all, where anyone can just posit anything they want. The opposite is the case. Good philosophical methodology leads us to accept reasonable and intuitive theories that are indicated by the evidence and reject wild and crazy speculative theories that are not.
In this spirit, if someone would accept a theory as crazy sounding as quantum mechanics without any scientific confirmation, this would be bad philosophical methodology. It's only in the realm of hard science that we can entertain and sometimes even accept such seemingly absurd theories. The ability to go to the laboratory and test scientific theories allows more theories to be taken seriously before they're tested and also limits the number of theories that are accepted after they're tested.
While it's true that from time to time science verifies and accepts seemingly crazy theories like quantum mechanics, this doesn't mean that our sense for a bad theory is baseless, or that we should now be willing to accept all wild theories. Of course not. In non-scientific areas, where we can't be guided by our predictions and testing, All we have is our rational mind's ability to differentiate between good and bad philosophy, between reasonable ideas that are supported and crazy ideas that are unsupported.
You know, Ellie, this conversation is a bit abstract, and it's been a while since you've given an analogy. Maybe it's time for a new one that doesn't involve any marbles.
Hey, what's wrong with marbles? You don't have to answer that. Let's try this analogy. In 1641, René Descartes proposed that perhaps all our observations are due to the machinations of a powerful and intelligent evil demon that attempts to deceive us into falsely believing in our perceived external reality. As wild as this may sound, this theory explains and is consistent with all our observations. How could we disprove such a theory? If you think about it for a bit, you'll realize that any evidence we would bring to undermine this theory and instead support the existence of a real external world could simply be chalked up to the ingenuity of the sneaky evil demon. Despite the fact that no amount of observation could possibly contradict the speculative philosophical theory, we all reject it as wild and crazy. Since it's a contrived theory with no basis or indication, it's bad philosophy.
The far more intuitive and direct inference from all our observations is the very popular theory that the external world actually exists, rather than the unsupported assumption that we're being tricked by a demon. Good philosophical methodology leads us to accept the simple explanation that's indicated by the evidence and reject the contrived speculation that some sort of conspiracy has created the illusion of a real world.
On the other hand, if the evil demon theory actually made new and surprising predictions, and these predictions turned out to be confirmed by observation, then we'd be forced to accept it as a true theory, even though it sounds crazy. Although it would have been untenable as a philosophical theory, it would be confirmed by the scientific method.
But Descartes' evil demon theory doesn't make any new or unexpected testable predictions about the world. All it does is give a much less intuitive explanation for things we already knew. That's not a testable prediction. Therefore, no one, including Descartes himself, believes the evil demon is real.
It goes without saying that even if we would translate Descartes' evil demon into the rigorous language of modern mathematics, it wouldn't change a thing. It would just be bad mathematical philosophy, not science.
The same would be the case if someone mathematically formulated the Greek gods of thunder, lightning, and rain. Even though these gods are invoked to explain the physical world, a speculative philosophical theory doesn't become science just because it's expressed mathematically. The bottom line is that to be science, a theory must make testable predictions.
Before moving on, we want to reiterate that the distinction between science and philosophy is especially important because of their different methods for evaluating theories, especially theories that sound crazy. In science, we entertain and sometimes even accept seemingly crazy theories because they can be judged by the scientific method. But in philosophy, we reject seemingly crazy speculative theories because they seem crazy and they can't be rescued by making testable predictions. Because of this distinction, it's incredibly important to honestly assess whether a particular theory is science or philosophy, so that we can employ the proper methodology for evaluating whether it's true or false.
Even though science and philosophy are different subjects with different methodologies, they can still complement one another. In other words, even though philosophical theories can't be tested experimentally, you can still arrive at true philosophical knowledge by applying good philosophical reasoning to scientifically verified facts. Nevertheless, it's important to remember that the process of reasoning from scientific facts to arrive at non-testable conclusions results in science-based philosophical knowledge, not scientific knowledge.
With this in mind, we must honestly acknowledge that the investigation into whether the ultimate cause of the physical universe is intelligent or unintelligent is science-based philosophy. While scientific knowledge can be used as a basis to find indications of an intelligent cause of our one universe, or in the opposite direction, to suggest an unintelligent measure for an infinite multiverse, neither of these theories is falsifiable. This is because neither theory makes any testable predictions.
But that's not something to worry about. There's nothing wrong with a theory being categorized as philosophy instead of science. However, once we recognize that this question is philosophical, not scientific, it's important to investigate it using good philosophical methodology. Without the check that empirical testing provides, a person's speculations can run wild. One false step based upon bad philosophical reasoning can send a person to the world of fiction and fantasy. This is true whether one is dealing with a theory of an intelligent cause like God or an unintelligent cause like the measure and laws of the multiverse.
Since the philosophical question regarding the universe's ultimate cause can so easily lead to imaginative conclusions, the best approach to answering it is by taking advantage of the fact that it's not an area of pure philosophy, but science-based philosophy. In other words, our investigation of whether the ultimate cause of the universe is intelligent or unintelligent can and should be built on tried and tested conclusions of modern science.
This is the approach we took in our first series. Based on the modern discoveries that our universe is fine-tuned, designed, and ordered, we presented 3 arguments that these features all lead to the straightforward philosophical conclusion that our universe has an intelligent cause.
Our first argument began with the discovery of modern physics that the constants of nature are fine-tuned. We then argued that this scientific knowledge directly indicates the philosophical theory that the specific fine-tuned values of the constants were chosen by an intelligent fine-tuner for the purpose of bringing about our complex universe. Similarly, the second and third arguments employed philosophical reasoning based on scientific discoveries of our universe's design laws and highly ordered initial conditions.
It's a testament to the efficacy of the scientific method that has provided rigorous knowledge that can serve as a basis for a solid philosophical answer to the question of whether or not the cause of our universe is intelligent. This makes the fine-tuning argument a prime example of good science-based philosophical reasoning.
Given the distinction between true science and science-based philosophy, it's critical that we determine whether the multiverse is genuine science that can be evaluated by scientific standards, or whether it's science-based philosophy that should be evaluated by philosophical standards. Only then will we be able to judge whether the multiverse is a valid explanation for fine-tuning.
At first glance, since multiverse makes no new testable predictions, and likely never will, it would seem that it's science-based philosophy rather than science. As Brian Greene writes in his book, The Hidden Reality, no one knows whether it will take years, decades, or even longer for observational and theoretical progress to extract detailed predictions from any given multiverse.
Wait a second, Aaron. Didn't we say in episode 7 that the multiverse makes a type of prediction since it claims that we're typical observers in a typical universe? And didn't we say that this prediction enables it to be falsified by episode 8's Boltzmann brain and grand universe problems? Doesn't all that make multiverse subject to the scientific method?
Good question, Ellie. If you recall, at the time, we made that point with 2 caveats. First, we were ignoring the essential fact that eternal inflation's infinities prevent multiverse from making any prediction whatsoever without introducing ad hoc measures. Second, even with the introduction of a measure, multiverse merely predicts that we live in a typical universe. But that's just predicting that we should observe everything we already expect to observe. It's true that this type of prediction exposes multiverse to being just plain wrong, since all the measures tried so far predict the typical universe is different than ours. Nevertheless, even if multiverse scientists would one day find a specially designed and fine-tuned measure that makes our universe typical, the prediction that everything is what we already thought it was isn't a new and surprising prediction that's characteristic of a testable scientific theory.
I hear that, Aaron. Given these points, let's assume, at least for the moment, that the multiverse is a science-based philosophical theory and judge whether it's good or bad philosophy. To do so, let's determine if the theory of the multiverse is indicated by the evidence, beginning with the evidence of fine-tuning.
As we explained in Season 1, the scientific discovery that our one universe is fine-tuned, designed, and ordered indicates an intelligent cause, not infinite randomness.
That isn't to say that an infinite varied multiverse couldn't explain and be consistent with fine-tuning, but only that multiverse isn't the simple, straightforward implication of fine-tuning. That's why multiverse scientists don't generally start with fine-tuning, but instead claim that an infinite varied multiverse is indicated by the scientific theories of inflation and string theory.
However, as we explained in episode 6 of this series, taken on its own, an infinite varied naive multiverse is a bad philosophical theory because it's a theory of the gaps that explains anything and everything. To rectify this problem, multiverse scientists must posit the existence of a measure that governs the probability distribution in the infinite varied multiverse. This measure limits the explanatory power of an infinite multiverse to typical universes and thereby opens the door for the claim that our universe is typical.
But, as we explained in episode 10, there's nothing about either eternal inflation or string theory that indicates the existence of any measure at all. The unjustified introduction of an ad hoc measure is a poor philosophical step that is not indicated by any science-based fact.
Based upon this line of reasoning that we developed over the past 6 episodes, when we judge multiverse by the standards of science-based philosophy, it turns out that it's like the untestable theory of Descartes' demon. They're both consistent with our observations, and they both even explain our observations. But the problem is that neither is indicated by our observations. Therefore, the problem with the theory of an infinite varied multiverse governed by an ad hoc measure is not that it's philosophy. That's fine. But that it's bad philosophy.
Before we move on, we want to mention a valuable side point. Even though the issue of whether the ultimate cause of the physical universe is intelligent or unintelligent is philosophical, is nevertheless an important question with significant ramifications.
For example, fine-tuning's evidence for an intelligent cause reintroduces teleology and purpose into the universe. In our opinion, the fact that over the past few hundred years, modern science has attempted to eliminate any objective basis for purpose has been a major cause of the gloom and malaise that has fallen over modern society. To many people, if the whole notion of purpose is artificially constructed by humans and is therefore entirely subjective, it loses much of its value and significance.
On the other hand, if one gains conviction in the existence of an intelligent fine-tuner that designed our universe with a purpose, this can shift one's entire worldview. Instead of merely occupying a meaningless universe, we can seek out our role in a meaningful universe. Instead of roughing it out in a universe devoid of any purpose, we can find inspiration to rise to the challenges of a universe in which purpose plays a central function.
Furthermore, the discovery that our universe was created by an intelligent cause for a purpose can serve as a foundation for a philosophically grounded system of ethics. This is especially needed given the confused and contentious state of moral philosophy that has followed in the wake of eliminating teleological-based ethics.
Fuller discussions about the significant implications of God and an objective philosophical basis for purpose and morality are beyond the scope of our current topic. We just wanted to make the point that just because something isn't science but philosophy doesn't mean that it's unimportant to real people who care about things like purpose, meaning, and ethics. Let's get back to how multiverse scientists respond to the charge that the multiverse is bad philosophy.
To some degree, multiverse scientists know that positing an infinite number of unobservable universes where everything possible happens sounds like a wild and crazy theory that isn't indicated by our observation of one fine-tuned universe. They also know that measures aren't indicated at all. For these reasons, they generally don't justify multiverse by claiming that it's good philosophy. Instead, they say that multiverse is science.
They start by arguing that eternal inflation and string theory aren't merely science-based philosophical theories, but that they're bona fide scientific theories. And since an infinite varied multiverse follows from these theories, they argue that multiverse is legitimate science.
If they're correct about this, then it doesn't matter that multiverse sounds wild and crazy when judged by philosophical standards. After all, if we were to judge quantum mechanics by these standards, we would no doubt conclude that it's wrong. Despite that, everyone accepts quantum mechanics as true, or at least something that approaches the truth.
The reason everyone accepts quantum mechanics as true is because we don't judge it as a philosophical theory or expect it to follow good philosophical methodology. Because quantum mechanics makes testable predictions, we treat it as a scientific theory and judge it by scientific standards of verification. And when we do that, it passes with flying colors.
In the same manner, if multiverse is truly science, then its philosophical weaknesses wouldn't make any difference at all.
In the next episode, we'll examine multiverse scientists' arguments that multiverse is real science.
Besides showing what's wrong with their reasoning, we'll also quote many prominent scientists who vehemently disagree with labeling multiverse as science.
We'll even get into the controversy about changing the very definition of science in order to accommodate the multiverse. All that and more, so stay tuned.